Welcome to This Explainer. Today, we're going to absolutely flip the script on the origin story of computer science and artificial intelligence. I mean, if you thought the foundational logic of modern computing was cooked up in some mid-20th century lab, well, you're in for a massive surprise. We're looking at a system of rules today that isn't just dusty history. It's a living, breathing algorithm that is literally shaping the future of AI right now.
So, who actually wrote the world's first computer algorithm? Now, your mind probably jumps straight to Alan Turing, Ada Lovelace, maybe John von Neumann. And that makes sense, right? We just naturally assume the algorithms running our digital lives were written in the 19th or 20th century. But what if I told you the foundational logic of computing, that highly precise step-by-step processing of data, was actually engineered thousands of years earlier? And get this, entirely without electricity or microchips.
Let me introduce you to Pāṇini. He was an ancient Indian grammarian living around the 4th to 6th century BCE in what is now northwest Pakistan. Widely hailed as the father of linguistics, Pāṇini developed this intensely systematized framework for the Sanskrit language. But here's the kicker. He didn't just write a grammar book. He built a generative system that perfectly mirrors the logic, structure, and architecture of today's software algorithms. We are, for all intents and purposes, looking at the world's first computer scientist.
Moving into Section 1, the ancient computer scientist. Let's dive right into how Pāṇini's legendary text, the Aṣṭādhyāyī, goes way beyond traditional linguistics and acts as a formal mathematical system of computation. This wasn't just a list of vocabulary words or conversational phrases. The renowned 20th century American linguist Leonard Bloomfield famously called Pāṇini's work one of the greatest monuments of human intelligence. And modern scholars absolutely agree. They view this ancient text as a completely unmatched intellectual achievement, because while modern Western linguistics only started turning toward this kind of formalization in the 20th century, think Noam Chomsky, Pāṇini had already mastered these concepts over 2 millennia earlier.
And the sheer scale of this thing is staggering. Pāṇini's Aṣṭādhyāyī is made up of about 4,000 extremely concise rules, known as sūtras, all strictly organized into 8 chapters. He was obsessed with what we'd call minimum description length today, basically extreme data compression. He stripped away absolutely all redundancy to create the tightest, most mathematically efficient representation of the Sanskrit language possible. It's honestly like the ultimate zipped file of human language.
Which brings us to Section 2, inside the language machine. So, if it's not your standard grammar textbook, how exactly does this thing run? Well, the Aṣṭādhyāyī's architecture operates exactly like a generative language machine. It uses deterministic production rules, recursive applications where rules feed right back into other rules, and precedence-based conflict resolution for when rules clash. It even has its own formal metalinguistic notation. Basically, these 4,000 rules function exactly like a modern software algorithm. You feed the machine a base root and a suffix, and it processes it step by step, churning out a grammatically perfect word while systematically filtering out the wrong expressions.
To put that into perspective, just look at the direct equivalency between Pāṇini's linguistic components and modern data structures. The sūtras, those are your deterministic production rules. The Dhatupāṭa acts as a massive foundational database of about 2,000 verb roots, similar to how his Ganapāṭa works as a lexical inventory. Then you've got Paribhāṣa, which are basically meta-rules governing the system's logic to keep everything self-consistent. And the Shifa sūtras function just like data arrays, layering everything from sounds to phonemes, morphemes, all the way up to sentences. He literally abstracted language into modular code.
Let's fast forward a bit in Section 3, the syntax of software. Let's see how this ties into the literal syntax of modern coding.
Okay, so in 1959, an IBM computer scientist named John Backus developed a metalanguage to define the syntax of a new programming language. You probably know it as Backus Now Form, or BNF. It's a foundational notation system still heavily used in computer science today. But here's the mind-blowing part. Scholars soon realized Backus's notation was structurally identical in power to the notation Pāṇini invented all those centuries ago. The overlap was so undeniable that in 1967, Peter Zelihe Ingerman basically said, hey, we need to give credit where it's due, and suggested renaming the modern standard to the Pāṇini-Backus form, just to acknowledge this incredible ancient invention.
Now into Section 4, powering modern AI. Because honestly, this isn't just fun historical trivia. Pāṇini's ancient architecture is actively solving cutting-edge problems today. You see, one of the toughest challenges in artificial intelligence is teaching a machine to actually understand human meaning, not just scrape raw text. Well, Pāṇini developed something called Karaka theory.
It's a framework defining semantic-syntactic correlations, meaning it maps concepts, like who the agent is or what the object is, directly to the sentence structure. This approach to morphological analysis provides modern natural language processing models with exactly the structured framework they need to translate human meaning into syntactic data that a computer can actually parse.
And this is a total game changer for machine translation right now, especially for what we call low-resource languages. Most dominant AI models today are huge neural networks that need mountains of data. But lots of South Asian languages, which share similar morphological complexities to Sanskrit, just don't have those massive digital datasets. So by integrating Pāṇini's rule-based decomposition of roots and affixes with modern machine learning, engineers can build highly precise, efficient AI models that don't need terabytes of training data. Pāṇini's rules are doing the heavy lifting for the machine.
But there was a catch, which we'll cover in Section 5, the final puzzle solved. Despite the absolute brilliance of the Aṣṭādhyāyī, a massive rule conflict bug had plagued scholars trying to run this algorithm for 2.5 millennia. Because Pāṇini's system is so immense, you inevitably hit a wall where two rules try to apply simultaneously to the exact same step of a word's derivation. Pāṇini did provide a meta-rule, Rule 1.4.2, to resolve these clashes. But, incredibly, for 2,500 years, scholars misinterpreted it. It led to all sorts of grammatical errors unless they patched in hundreds of their own messy, subjective exceptions. That is, until 2022, when an Indian PhD student at Cambridge, Dr. Rishi Rajbapat, finally decoded Pāṇini's original algorithm, turning the ancient machine on flawlessly for the very first time.
Rajbapat's solution is just stunningly elegant. For centuries, the assumption was that Pāṇini meant that in a conflict, the rule that appears later in the book's serial order wins. Well, Rajbapat proved that was totally wrong. He showed that when two rules conflict, one applying to the left side of a word and one to the right, Pāṇini simply wanted the rule applicable to the right side to win out. So take the word manthrai. You input mantra on the left and the suffix bis on the right. Boom, two rules conflict. But by just choosing the rule applicable to the right side, bis, the system flawlessly outputs manthrai without any extra tweaks.
The result of this fix is profound. As Dr. Rajbapat himself put it, Pāṇini had an extraordinary mind, and he built a machine unrivaled in human history. The crazy realization here is that scholars had been muddying the waters for centuries, adding all these unnecessary patches. But Pāṇini's original code, it was completely self-sufficient, a mathematically flawless machine from day one.
So why does this matter for us today? Because with this 2,500-year-old bug finally squashed, we now possess the exact flawless algorithm that runs Pāṇini's grammar, which means we can potentially teach this perfectly structured linguistic system directly to computers for the very first time. We're talking about finally merging ancient rule-based clarity with modern machine processing, creating AI systems that are transparent, ethical, and incredibly precise, without the whole thing crashing from rule conflicts. Honestly, it completely shatters how we view the timeline of human innovation. I mean, if the precise algorithmic blueprint for computing and natural language processing was just sitting there, hidden in a Sanskrit text written 2,500 years ago, it really makes you wonder, right? What other advanced technological secrets are still waiting to be decoded from our ancient past? Thank you so much for joining me for this explainer. Keep questioning, keep digging, and I'll see you next time.